Good morning everybody, welcome to today's live. I'm going to talk a bit about the Poseidon today. Just wait for you all to join the room. Morning Dave, how you doing buddy? Morning Sam. Morning Mr. Turner, how you doing dude? Morning Ian, how you doing from the Philippines mate? Nice to see you. So 12 of us at the moment, just give it another minute for a few more people to join and we'll get started. As you can see we've got the prism arrived with us the other day, so we've got a brand new CE prism to show you guys in the next video. The CE prism is really a new release, so it's nice to be able to get one in full spec, you know, with the back mounted counterbalance and all the nice toys on it. So we've got the Prism 2 next week, and that's here now, just been built up from a brand new machine, so it'll be quite a nice cool thing to see. Morning Brian, good morning Ludo. Val, how you doing dude? How's life in Newquay? I thought you guys might be getting back in the sea by now, unless it's too windy down there I guess. Just another minute, we'll wait for everybody to get in till 5 past and then we'll kind of start. Yeah, no worries Ian, it'll be on our live Facebook for a couple of days yet. So we can, at the end of the series, you can either watch them all back or watch them one at a time, no problem at all. Morning Max, morning George. It is 5 past by your watch. I started 5 minutes late, so. Okay, so let's get started. Today we're going to discuss the Poseidon 7 and 6 rebreathers. The 6 and the 7 are very closely related. The difference being is the electronic module. Most of the external compartments are relatively similar, external parts are similar. So I'll just explain as we go through the difference between the 6 and the 7. The actual unit we're going to build for you today is a 7, so it's a Poseidon 7, but you'll see as we go through some modifications that have come from the 6 to the 7. So let's start by talking a little bit about the Poseidon and why it was designed. So the Poseidon was designed as a recreational rebreather. A rebreather that was designed for anybody to use with very little training. So we could even teach people to dive who'd never dived before to start with a rebreather. That meant the philosophy had to be super simple. Poseidon were looking for a company to build a rebreather for them, and that company could have been Draeger, it could have been one of the other manufacturers, could have been AP. In the end, they went to a company called Se7en. Now, Se7en were world renowned for making the Mark V rebreather and the Mark IV, which are basically the size of a refrigerator on your back, and were designed for really deep diving. The difference was when they said, we've got this new project, we want to teach people who've never dived before, we want to make it completely hands-free to dive a rebreather, and we want to make it so simple that the user has no input to the rebreather at all. They just need to breathe in and out, kick their feet, just like they do on open circuit scuba. Se7en turned around and said, well, that's impossible, we can't do that. In the end, Poseidon bought Se7en and said, now we own you, you're going to do as you're told, we're going to need to build a rebreather that suits anybody. And they spent an absolute fortune on it. So there was you know, a hell of an amount of money spent on designing the rebreather to make it as simple as possible. And that's what we were left with. We were left with the Poseidon 6, which was the first, let's say, recreational rebreather designed to be used by anybody at any point in their career, and would be completely, you know, hands-free and autonomous, look after itself. So using modern technology. Though they called it at the time the rebreather revolution, which was designed to put rebreathers in the hands of anybody. And it did work. There was a lot of Poseidon sold in the early days, the Poseidon 6 and 7. but it was always hampered by the fact that it didn't go any deeper. It was originally limited to 40 metres with a green recreational battery and without decompression. That meant that a lot of people would say that it was a lot of money for something that was limited in its application. It wasn't designed for those people, but it did put a bit of a sour taste in people's mouth when they were reading about the rebreather. So it's always good to understand where it came from. When you think about the Poseidon rebreather, when we look at its development through the years, it's had lots of add-ons and upgrades that make it capable of doing something that maybe wasn't what it was originally designed for. So when you look at the JJ was designed with one job in mind, which is trimix rebreather diving and deep. Whereas the Poseidon was designed to be a recreational rebreather, a rebreather that's simple and has no input in the 40-metre recreational range or even shallower. So there's some unique features about this rebreather that don't exist on other rebreathers, and there's some features about this rebreather that are actually much cleverer and much more advanced than any other rebreather on the market can do. Of course, you'll probably know the stories with lots of advanced technology. Potentially comes a lot of snagging points as you go through the build process. And in the early days of the 6 rebreather, there were a lot of kind of software issues. Those got developed, and the 6 turned out to be a very, very solid, stable rebreather. And it did its job in the recreational range pretty much perfectly. There was liverboards with 10 or 15 of these rebreathers on them. People could just fly out, rent the rebreather for a week and go diving. So what are some of the unique features about it? Well, one of the unique features about it is the way that it uses its cells. Most other rebreathers have 3 cells, or like you saw the other day, 5 cells in the Revo. But at least 3 of those cells are normally to do voting logic. And the voting logic is, if 2 cells are close, the likelihood is that they're correct. If one cell is then outside of the range of those 2 cells, it votes that cell out and uses the average of the other 2. Which in most scenarios is pretty good average. Gives you good odds of making sure you know what's in the rebreather. There are the times though where you can get 2 cells which current limit, so the amount of voltage that they can produce is limited, and in that scenario your machine would vote out your one potentially good cell and pick up the other 2. So to eliminate that, Poseidon decided to work with 2 cells. One cell would be the cell that you're diving on all the time, and the other cell would be its validation cell, so the cell it checks itself against. So 2 independent sets of monitoring. And what it would do, it would not only monitor the exact PO2 of one cell, compare it to the next one, it would monitor the rate at which the voltage increased, decreased, and the speed at which that increase and decrease happened. And as it did that, it would be able to tell if the cell over time, it was losing its linearity when compared to the other cells, so the cells weren't moving together with each other, and it could vote that cell out. And we'd see it on the screen as either a C1 error, which means there was confidence in cell 1, a C2 error, which means there was confidence in cell 2 error, or C0, which means it didn't have any confidence in any cells. Well, how can it have confidence in no cells? The reason is it's got another really unique process. Every 5 minutes during diving, the machine would inject diluent directly onto the cell face, and it'd be like a little psh. It's really a thimble full of gas. It doesn't affect your buoyancy, it doesn't make any difference to the rebreather, and it's directly on the cell face. Now, the really complex algorithm inside the electronics detects that this is a known gas, uses its pressure sensor, so it's known as it's a known depth, and checks its calibration throughout the dive. So this rebreather technically checks its calibration every 5 minutes while you're diving. So the cells can't deviate. If you get moisture on cell face, that gas blowing on will blow the moisture off the cell face and then recalibrate itself and check. In the event that the cells start to give confidence errors, it will do that validation check more often. Number 1, to clear the water off the cell face if potentially there is any, but also to get itself back aligned and into calibration. No other rebreather on the market does that. Most rebreathers on the market you calibrate before you go diving, and once you've calibrated those, you then go into the water, and at that point you need to monitor the cells as they increase and decrease in voltage. There's no way to then recalibrate them. You can do a manual diluent flush, which means you're going to inject a known gas at a known depth and look to see if the PO2 is what you suspect it should be. But this machine's doing it in the background automatically. It also is not very wasteful on gas. To do a diluent flush on a normal rebreather, to clear that volume of the high PO2 gas and bring it down to diluent, firstly, it affects your decompression schedule because you've changed the gas in the loop. Secondly, you've wasted quite a bit of diluent, putting 4 or 5 litres of gas in to try and blow out all of that high pressure gas. and get your reading stable. Once you've got your reading stable, the machine's going to want to inject oxygen again to bring it back up. The Poseidon puts a thimble full of gas directly on the cell face and looks at that instant reading. If that instant reading is not what it expects, it tries again. But it's not pumping enough diluent in to change any of the loop because the gas injection is directly at the cell. So it's quite a unique process to the Poseidon rebreather, and it means that during the dive it can have very good confidence in the two cells that it's got. With that in mind, we actually only really dive with one cell, and the other cell is just there to check it and back it up. There is an option to add a third cell onto this rebreather if you want to have an external, completely separate computer monitoring the rebreather, but generally those two cells will be very good because you've got a permanent confidence reading if there's any calibration. However, what we found over time was that cells don't act as we suspect. From time to time the voltage drops off for no reason. From time to time they have little spikes in voltage, and that is picked up by this system. So it took a bit of time as the software developers were getting more and more data to realise that cells aren't quite as accurate as we imagined. They're very fickle things. The smallest knock or bounce or change in temperature would make the spikes and stuff appear in different places and in different cells at different times. There's also an offset. Depending on where the cell is, actually in the head compared to where the oxygen is injected, there's a delay between one cell and the other cell. And if you imagine you're trying to monitor the two cells going up and down with each other, you've got to try and get that offset right. That offset is also affected by the rate at which you're pushing gas around the loop. So it took a bit of time as they were getting more and more dive data to get this algorithm as close to perfect as possible. In the end, I think they did a very good job, but it means that from time to time there was a bit of a bad reputation with the Poseidon rebreather that the cells were a little bit unreliable. And I don't think it was the cells themselves that were unreliable, I think it was the algorithm just learning over time to become better. This machine is available as a recreational rebreather, all the way up to a 100 metre rebreather, and actually the battery's okay to 154 metres. So the machine can go all the way to 154, but the CE certification is up to 100. Different versions available. You have the Sport. The Sport is like a stripped down light version, going to cost you about £5,200. The recreational version, which means it comes with the wing and everything, and the back case makes it look a little bit prettier, that's 6.2. The tech version, with all the, it's got M28, which is another off-board computer, the standard on-board computer, and the technical wing, the manual edition counternoise and all the upgrades, that's about 8,004. If you want to go and spec the highest spec you can, it's a little bit like when you go on the Apple store. You can say, I want one of those, and I want one of those, and I want to add one of those, and you can add two M28 computers, and you can add something called solid state cells, which we'll come to in a minute, and you can add something called a C-pod, and by the time you've configured your rebreather all the way up, you can get up to about £13,000 with the Poseidon rebreather. It's got all the bells and whistles you can possibly imagine on it. So, those custom configs are also available. It is probably the rebreather with the most upgrades possible. You can upgrade the smart batteries, there's five smart batteries available. You can upgrade the counternoise, you can upgrade the wing, the harness, the plate. When you buy the rebreather, it generally doesn't come with a backplate harness and wing at all, which means you can fit it to the system you've already got. You can add things like we said, the third cell holder, you can add the C-pod, the solid state cells with multiple computers that plug in via a CAN bus system. So there are potentially, hundreds of configurations of Poseidon rebreather out there. The other nice thing about this rebreather is its weight. As you can see, the can itself is super light. This is just an aluminium tube with a plastic head and a small lightweight aluminium handle. When I pack the rebreather down, not only is it super small, if you compare this to something like a JJ, or you compare it to an SF2, it's super small. We can actually get the weight really down as well. So we can get the weight under 10 kilos and get it into hand luggage. I used to travel with this rebreather fully assembled, well not assembled, but all the pieces of the rebreather without the cylinders in my hand luggage. You get it under 10 kilos. So that's a really nice part of this machine. It does mean though that you're going to need a little bit of weight when you dive into the rebreather compared to some of the others when you get there, but you're not travelling with that, so it makes it a little bit easier. Okay, so how does it work? We're going to go through now and build the rebreather up. Of course, we've got our SSI Poseidon checklist that we're going to go through, make sure that we build the rebreather correctly, and I'll start to explain the parts to you. I'm going to build this machine today without a backplate harness and a wing on. So inside this groove that you can see on the backplate here, You'd have an 11-inch adapter, so that gives you a normal 11-inch spacing. You can put a standard backplate or harness on wing. You can also put a BCD, so your normal recreational BCD. You can just cam band around this can, and you can put that on your back as well. So it's quite versatile in the configuration options. You've got to understand that the rebreather is going to come in a few parts, and as we go through, I'll show you each individual part as we build it up. The first thing to do is I have two options. I can either A, fill a repackable scrubber canister, or B, I can buy a pre-packaged canister that I put directly into the machine. At launch of the rebreather, and for the first kind of 9 years of the rebreather's life, you would need to buy a Poseidon, Molecular Products Poseidon authorised canister of softener pre-packed. They're a fantastic idea. They remove almost all the problems with channeling, they remove almost all the problems with bad packing, and they really are super convenient, which is what you would want if you wanted to dive rebreather for fun, just for recreational purposes. Problem with it is they're a little bit expensive and a little bit hard to get in remote locations, plus a bit of a waste of plastic, which isn't great for our environment. So eventually Poseidon have reissued the ability to be able to use a repackable scrubber canister like this one, and this means that you can fill your own scrubber material exactly the same as you can on the other rebreathers. It takes a very similar quantity, about 2.3 kilos of softener line, and it's got the same duration as most rebreathers, which is a 3-hour CE certification. So that's our repackable scrubber. Again, we won't show you today. If you do the course, you'll learn how to pack the scrubber canister. So this is option A, fill the canister with softener line or verify there's a sufficient time for diving, which I've done. The next step is to insert our pineapple sponge into our bottom plate. So this is the bottom plate of the rebreather, and this sits in the base. When we exhale gas, they will come down the outside of the scrubber, through these holes here, and then up through the middle of the scrubber. In the middle of the scrubber, of course, you have the chemical reaction. You have the CO2 removed, and that releases moisture, and it releases heat and creates chalk. That moisture will then drip through the scrubber, and we want to catch it so that we don't end up with loose liquid in the base of the scrubber in case you invert and then that liquid rolls around. So in this rebreather we have a sponge. Like Chemek called it on the Revo, the oxygen clean CE approved moisture absorbent. You can call it the same thing, but basically it's the pineapple sponge for the Poseidon. We smell it, just make sure that it's clean and been washed, and it fits here onto our base plate. That little white thing just keeps it in place. That traps any moisture. We want to make sure there's no moisture in there for a couple of reasons. If there's lots of moisture in the air, that can then condense on the cells. If it condenses on the cells, and on the face particularly, we can get the cell technically freezing, which is where gas can't pass onto the cell because of the hydrophobic membrane. You can see here we've got an O-ring, and that O-ring is designed to hold the scrubber in place. It's not a critical O-ring. It doesn't actually do anything for the gas. It just keeps the scrubber from falling off. On the base I have two O-rings, and those two O-rings there seal against the bottom of the rebreather and stop any water entering. So these two are critical O-rings. I need to make sure they're in good condition. Inspect and grease the three O-rings. So if required, just take my sharpened little paintbrush, take out these O-rings. Again, with all O-rings, what I want to do is just make sure that I clean them with my fingers, remove any grit or grease or grime, get a bit of tissue. The same thing, just give them a little clean off. This machine is, again, this machine has just been serviced, so it's in good condition. Put a bit of grease on the top. And again, we're looking for shiny O-rings, not greasy. You don't want big lumps and chunks of grease. All that's going to do is pick up contaminants and stuff from the floor and the water, which is not what we want. We'll pop that in place. So that one was super clean. We have the two sealing face O-rings and then the O-ring that holds the scrubber can in. Just a little tip, one of the things I don't ever grease is I don't ever grease this O-ring. When I fit my canister on, I want to make sure it stays solid in there to allow me to push it into the base of the rebreather. To do that, I want a good friction fit here, so I don't actually grease this red O-ring. That's a personal little tip from me. Okay, so we've now got our little base, so hopefully you guys can see that there. And I've inspected and greased my O-rings. Now I'm going to fit the scrubber to the bottom plate. So my scrubber is down full with softener line. I just inspect the base, make sure there's no nicks or damage, and then I place it on top of the bottom plate that I've just made. That fits together like so, as you can see. Oh, we lost a screw there. So that all fits together like that. The next step is to inspect and grease the 2 top hat O-rings. So this is our top hat, and it fits on top of our scrubber. Okay. So like we said, when we exhale, the gas is going to go down the outside of the scrubber, through those holes in the base plate and back up and out this centre hole. If the gas is allowed to mix from the outside exhaled gas with the incoming clean gas, that means the gas could technically bypass the scrubber. So these 2 O-rings are critical O-rings. As you can see, they're red. They're red so that you don't lose them and you make sure that they're installed. Take them out and you can see we have that O-ring, and here we have this one. There's been a couple of fatalities because of these O-rings not being in place. So they changed them from black to red to make sure that the diver definitely makes sure it stays in there. Also, the new O-ring, if you look, that doesn't come out there very easily. It doesn't fall out. Okay, you have to really give it a good bash for that O-ring to come out. So what I'd recommend to all my divers is whenever you take this out to clean it, you hold both pieces in one hand and then you put it back together. The biggest potential problem is you put this down, you clean this and put it somewhere else, and then you pick this and you put it in your rebreather. And now there's going to be no CO2 seal. So make sure we put this top hat O-ring into place. There's a space on the top for a pineapple sponge as well. Very early rebreathers had a pineapple sponge on the top as well to collect any moisture that was condensating around the electronics. What we found was as the machine heats up through your normal breathing process and the CO2 absorption, that moisture would evaporate again and become actual condensation again. So we removed that and actually let solid water collect here, because actually solid water is much less likely to evaporate than when being held on the sponge. So we took the sponge away and we leave that without the sponge on the top now. So you take this, inspect and grease, and place it on top of the scrubber canister. So we've got it built on the top. So now we've got our fully ready package that we're going to insert into the base of the machine. I'll take the time now to show you the machine itself. Okay, so this is the top of the rebreather. You can see here, it's the Poseidon Discovery, 2009 was the CE date and serial number, and this is the EN number. We've got an aluminium body of the can with welded brackets on it that allow us to attach our cylinders. It allows us to attach our backplate harness and wing, and it's got helicoils in the top here that allow us to attach this, what we call the Mickey Mouse head. You can probably see why it's called the Mickey Mouse head. It looks a little bit like Mickey Mouse with the ears. The nice thing about this is these ears are threaded so that where the hoses fit. If you were to damage one of these, you would undo this screw in the inside, and then you would be able to remove that ear, replace it again, and that would mean that this, just because you threaded this doesn't mean you have to scrap the entire can. Same thing with the top here. Where the electronics module fits in, this is a smooth sealing surface. If this was to get damaged, you wouldn't get the seal anymore. You could undo these top screws and just replace this part as well. So it's quite modular in that if something gets damaged or broken, it's very easy to change it in the field. If we look inside the can, we can see that it's plastic coated aluminium, and you need to feel around the inside. Where this lip is, the lip to the outside of the case is where our O-rings are going to sit. They're our sealing face O-rings, so we need to make sure that's in really good condition. If you want, and you're in a warm country, sometimes it's a good idea to just pop a little bit of grease on there so that the scrubber pulls in and out nice and easily. The next most important thing we need to look for is, if you can see through the base, you'll see what we call the spider. And this spider here gives the sealing face for the CO2 O-ring. So when we push the scrubber cartridge in, that top hat presses onto this spider and creates our seal. It also, I don't know if you're going to be able to see this very easily. Let me have a, okay, here. So you can see here we have a tube, and this tube has a connection point with a red O-ring. That's also a critical O-ring, so we need to make sure that that red O-ring there is in place. That red O-ring connects to the gas injection system and allows oxygen to be injected at the right point. The oxygen is injected, it goes through that little tube in that direction and gets injected into here. So it gets injected onto the gas that's before the scrubber. That means that the gas is injected, it's then mixed as it goes through the scrubber and comes out to the top. Okay, so we've got that gas injection point there. what we can see is if this O-ring isn't in place, or if this is damaged, during your diving you'll see the oxygen levels spiking every time there's injection, because the oxygen is then injected right next to the cell face, and then it makes the oxygen spike during descent. So we need to make sure that that red O-ring, which is a critical O-ring, is in place. It's got a little bit of grease on it, which it has, and is in good condition. So we're happy with that O-ring there. The gas path. This is a left to right rebreather, the same as the JJ. So different to the SF2, different to the Revo. This is a left to right rebreather. So this means you're going to inhale from the left hand side and exhale to the right hand side. So as you exhale, it's going to go down this way, and as you can see, if I put my finger through the base, you should just be able to see my finger wiggling down there in that bottom corner. That's where the gas is going to come out from the exhale side. It'll pass down the outside of the scrubber, up through the base, and then it'll come up, and if you see my finger this side, it'll come into this Mickey Mouse head, and then out in this direction here, which again, turn it over so if you guys can see, will come here. So once it's out the Mickey Mouse head, and it's been analysed, oxygen's been added, it will then come to this side here, and then back through to the diver. So the way that the machine's designed is that the gas path is all sealed internally. The only thing we need to worry about is that this top hat O-ring that we've made sure is in place here is in good condition and settled in place. So let's just take a quick question from Sam. Once built up, I imagine it's a bit more of a faff to change the scrubber when inserted from underneath. No, actually it's not, it's quite easy. With this rebreather, it's a lot simpler than other rebreathers. With most other rebreathers, you have to remove the electronic head. So you maybe have to take off first stages, disconnect oxygen fittings, remove different types of connectors. So you have to remove the electronics module. With this rebreather, because we have an access door from the base, all we need to do is lie the rebreather forward, undo the 4 screws, we can remove the scrubber cartridge and insert another scrubber cartridge without affecting the rest of the integrity of the loop. Okay? We still need to do a negative and a positive test because we have opened our loop of our rebreather, and we still need to confirm it's functioning properly. But it is quite a simple process, and actually maybe one of the easier processes for installing the scrubber, probably along with the Revo, which is a very similar design, isn't it? If we remove the back cover, we can quickly get to those scrubbers. So now the next step is we're going to insert the assembled scrubber canister into the main unit, small spacing towards the back of the unit. Now what do we mean by small spacing? If I show you from the bottom, you can see these are our thumb screws, and these thumb screws, if you look at them, they just fit into the helicoil. These thumb screws, we have a small space in here and we have a large space in here, and that means that when it's on the back of the diver, this is going to be the upright position. Yeah, so we have the small spacing at the back. To do that, I find the easiest way is to settle it there. I'm going to lift the rebreather over the top, line up everything so it's all nice and in place, and then just put a little bit of weight on top. That's perfect. If I was to be doing this on a boat, I would lean my machine forward onto its front. I would then remove the scrubber canister like this. It would be sitting on the wing and plate and harness, and then I would be able to insert another scrubber again from the base, just pushing gently as I go, and that makes sure that it's then fitted into the base of the cam. Like Luke says on our comments there, it's really nice if you are diving kind of on a rib or on a boat where you're going to sit in with the unit, that you have a stand as well. Because of the shortness of the rebreather, it can mean that the weight is quite high in your back, and then when you sit down, you can't actually get that base of that rebreather to settle. So a lot of people go for a stand as well. Always, if you're looking for a stand though, try to make sure you find a stand that doesn't impact your ability to remove and repeat and put back in the scrubber. A nice one is the stand that's available from Kent Tooling. The Kent Tooling stand is really fantastic. Builds either around the outside the whole machine to protect it, or fits on from the base with a leg system, a lot like we see on the JJ. A bit like stuff in a turkey. Yeah, you're right, Sam. So we've now got to tick off that. Finger tighten the bottom plate locking nuts using the same torque for each bolt. So of course, like all bolts, we kind of do these finger tight, but we're going to do them in opposite corners. I'm going to tighten one a little bit, tighten the other a little bit, tighten the other a little bit. Remember, we're putting a plastic plate into a rebreather here, so we don't want to over tighten it and snap the plastic plate. We want to make sure that it goes in nice and gently not pinching any O-rings as we go. You'll figure out that it will stop. If I bring it towards you now, you can see that in each corner where my screw is located, it's actually stopped now. There may still be a small gap here, and there may still be a small gap here, but this is just because it's plastic and it will deform ever so slightly. Our two O-rings are a good way inside and they're well sealed on that sealing face, so we don't need to worry. It's just a case of when you get it tight, you need to make sure that all four corners are then touching. That means your rebreather's nice and sealed. So we've got our built package now, and we can tick that off. The next step is to label and analyse our cylinders. So here's our two cylinders for today. A difference that you'll notice with this rebreather than we've had with our other rebreathers you've seen so far is that this on the oxygen side is the M26 fitting. So it's not the normal DIN fitting that you see on your normal regulator. We have DIN here on the diluent, but on the oxygen side we actually have an M26 fitting. This is, again, it's a mechanical interlock to make sure people don't get the cylinders on the wrong way. The first stage fittings are different. A M26 regulator will not fit into a DIN, and a DIN regulator will not attach properly to an M26 cylinder valve. So even if you get the cylinders attached to the machine the wrong way, you won't be able to put the first stages in. So it's another way of mechanically making sure that the rebreather is assembled to the right specification. As before, we're going to need our analyzer. Make sure it's nice, it's calibrated, which it is. A bit lively that valve. Turn on the oxygen. So just going to analyse the oxygen. Quite often it's a good idea to analyse the oxygen first. Just means you can see an analyzer go all the way up to 100%. If you know it's reading 100%, you know there's no problem with the cell being limited. So there we go. We have 98%, 98.9% oxygen there. So I'm going to mark that up. 98.9, maximum operating depth 6 meters. Same thing on the diluent side. Now, it's critical that you analyse your diluent accurately on the rebreather. Okay, just as critical as the oxygen actually, but you tell the rebreather what your diluent is. It is then going to check that. So it's going to analyse the diluent itself based on what the oxygen was, and based on what the oxygen diluent is, it's going to analyse the oxygen. So it checks the two gases against each other. If there's a small mistake, you're 1 or 2% out on your oxygen, and the oxygen percentage in the diluent, it will fail the startup tests, and that's caused people a little bit of aggro in the time. When you've taken your cylinder to a dive centre, they've accidentally kind of put in 1 or 2% oxygen while, you know, maybe it was in the filling line, and that caused the oxygen percentage in the diluent to not be what the Poseidon expects, which means it doesn't start up. And rightly so. If the diluent isn't what you expect, then the decompression calculation isn't going to be accurate. So it needs to be right. But it's just because we're so used to being 1 or 2% here or there, it doesn't really matter. But with the Poseidon being so accurate, we do need to make sure that our diluent is exactly what we think it is. So I'm going to analyse the diluent now. Okay, and my diluent is 20.9, so that's exactly what I expect. And the maximum operating depth for that is going to be 66 meters. Super. So those cylinders are now marked and analysed. If my diluent wasn't what was already programmed in the computer, I would use a PC to connect with Bluetooth to the electronics and tell the electronics that the diluent is now, you know, whatever percentage it is. So I need to tell the machine what percentage of oxygen and diluent I've got. So they're analysed. I can write my gas mix here as well. 98.9, and diluent was 20.9. And a pressure check them just to make sure we've got some gas. Yeah, you can actually reduce the oxygen percentage right down, and you can increase the diluent percentage up or down as well. It depends a little bit on your battery though. If you've got the standard recreational air battery, you're only going to have air diluent. But if you've got one of the technical batteries, then you can choose your diluent in the range that battery allows. We've currently got the deep battery, which is black in colour, and that deep battery allows you to use any gas available at all. Yeah, Luke, I think you should get your rebreather out, mate. What I suggest, though, is to make sure you get your rebreather to an authorised service centre. Just get it checked over properly, as you know. Well, that's an M26 fitting. I need to get an M26 adapter. Just a moment. So yeah, just get your rebreather over to a service centre. Just get it checked out. Make sure your cells are in date. Just reanalyse your gases, make sure everything's good to go. Do a nice simple check dive, mate, before you get in the water. This time of year, with us being out of the water so long, it's always a good idea to err on the side of caution. You're right, Sam, the battery does control the type of diving you can do on this unit. And so as you upgrade in your career and your diving, you can upgrade the battery as you go. Okay, good, so 180 bars. Put that up there. Quite a long thread, that 300 bar one. Let's put it out. Okay. So now I'm going to write down my pressures. Okay. And the last step is to attach them to the unit. So again, like before, left lean and rich right. So we're going to put the oxygen on our right hand side as we wear the unit, and the diluent on the left as we wear the unit. One of the things you'll notice for this rebreather is in this configuration that we've got here, the valve is pointed up. In lots of other rebreathers, the valve is pointed down. Just a second, let me get Will. Will! Yeah. Tassos at the door. Tassos is at the door. So we make sure the valve is pointed up. With this configuration, you're not designed to really shut down the valves. You can shut them down over the top of your head if need be, but the idea is that in a fully recreational configuration, these will be in the upright position. So when they're on, they're on. That means underwater you can't turn them off, accidentally isolating one of your gases. So they're in the upright position. They're a bit hard to reach in that position. So normally most rebreathers, the valves will be in what we call the inverted position down in the lower part of your back, which is really easy to reach. As an upgrade, this rebreather can come with a inversion kit. So you buy a set of hoses that make all the hoses longer and route down into the downward position. Okay, but as we've got it configured this way, we've got it configured in the upright position, the more recreational position. So nice and straightforward. If you've got the quick release clamps, you can just put them on. We haven't got any Jubilee bands that fit this cylinder at the moment, so we wouldn't use those. We're just using the cam bands, which are another option. So put the cam bands onto the rebreather, one on one side. We actually lift the rebreather up slightly. Something like that. In fact, I'll just keep it down so it's a little bit easier for us to work with. And same thing then on the diluent side. But I'll just get a little bit of tape. I'm just going to get a little roll of tape. One of the tricks is to lift the rebreather up. Because we don't have a backplate and stand and stuff on, it makes life a little bit more difficult, but so you guys can see, put my oxygen on, then on the other side I'm going to fit my diluent. Make sure it's nice and solid. Okay, good. So now we've got the cylinders attached to the rebreather. You can put any cylinders you want on the outside of this rebreather. You could put 7s on, you could put 12s on if you really had to. It comes with 3s. It can come with 3s that are aluminium or 3s that are steel. The aluminium ones are much lighter, but they do mean you need a little bit more weight. Yeah, so the left and the right, I think I managed to flip the video around, so it probably looks right to you guys now, which is good. So we've got it all set with our cylinders on. I can tick that off on my checklist. The next step is to inspect the breathing hoses. And these are my breathing hoses. Again, because this machine was designed as a recreational rebreather for simple diving, all 4 of these hoses are exactly the same. There's no different threads, there's no different lengths, there's no different fittings. I can put this one in any place and this hose in any place, and they're all exactly the same. If you're a smaller person, you can buy slightly shorter hoses, but they are still the same. It wouldn't matter if you accidentally put one in the wrong place, it just meant it would be slightly shorter. These hoses are quite strong. They're a smooth bore design. Okay, even though they've got convolutions on the outside that allow the hose to move, they're smooth bore. That smooth bore is really nice because it removes the amount of moisture that you can get trapped, stops that gurgling sensation, makes the loop easier to clear, and means that the machine has got a slightly better work of breathing because the gas doesn't cavitate as it passes over those convolutions. They're very strong, so you can't actually damage these. They've got a steel lining running all the way through them, so it's even though it looks a little bit flimsy, it's a really strong design. On the end of each one, the nice thing about this rebreather, to check the O-rings, all I do, I just pull down the fitting, and that exposes the O-ring 100%, so I can see it. I can get that O-ring, I can just push it with 2 fingers and pop it off. Check that O-ring and make sure it's in really good condition. So the O-rings are nice and easy to be able to access on this rebreather. You'll notice that it's got neoprene covers built in, and that's designed to stop the condensation and keep the temperature of the loop up. So it's got a built-in kind of temperature saving device on the outside, and they're a neoprene cover. Can trap a little bit of air as you start your descent, so it can look like bubbles. You just need to wait for that to go before you do your bubble check. So we're going to check the O-rings are in good condition. 1, 2, then I'm going to put my finger inside, just run my finger around and confirm the inside is clean, smells clean, looks clean. Same on the next one, just have a look inside, make sure it's nice and clean. O-rings on both ends, good condition. Put my finger inside, have a quick look, that one's nice and clean. Same with these ones, have a look inside, nice and clean. Finger check, O-ring check. A little bit of hair there, that's gone. And I'll clean this slightly greasy, which is what we're looking for. Everything's in a nice condition. So, one of the other nice parts about this rebreather is that all of the fittings where the hoses connect to are slightly chamfered. What that means is when it comes to actually fitting the hoses, you only need to put them in place and start to screw. That chamfer will drag the O-ring inside and naturally trap it in. So it means the O-ring doesn't normally splay out on this rebreather. If I want to fit a hose, there's a couple of ways I can do it. I can either push the locking ring back and push the hose into place like so, and then I'll fit the locking ring. That's one option. The other option is to just put it on the top and use the locking O-ring to draw the hose in a nice flat position, so there's even less chance that your O-ring is going to pop out. So by design, it's designed that everything fits nice and smoothly, nice and easily, because again, we wanted this to be done by people who are not so technically minded, let's say. So there's our 4 breathing hoses. They're all inspected, 2 O-rings per hose. The next step is to attach the rear breathing hoses, inhale and exhale. Maybe lost the machine there. Forward. Should maybe have got the stand out for it before we started, but there you go. Got one more. Okay, good. So attach the rear breathing hoses. So I'm going to put the one. This is our exhale side, if you remember. The exhale to the right, fit that one. And this one is our inhale side on the left. Put it into place like so. Just going to tighten that up. And again, I only go just until it stops. I don't tighten these, I don't put any pressure on them at all. Their only job is just to stop the O-ring being pulled out. The O-ring's got a long way to go before it's pulled out, so just a little tight, that's all it needs to be. If you go too tight, when the temperature changes, potentially the size of it will change and you won't be able to get it off later with cold, wet hands. Okay, the next step is to inspect our T-pieces. This machine that we're going to show you today these are the recreational front mounted counter-lungs. So these sit on the top of your shoulder. The bubble of gas that you're breathing from is technically on top of your shoulder, so they're sort of top of the shoulder more than front mounted. Front mounted would be more here, whereas this is top of the shoulder mounted. You want to make sure that this hole here is aligned with the side of the face with the ears. So they're a top of the shoulder counter-lung. That bubble of gas you're going to breathe from is going to be right here on the top of your shoulder. So because we've got those counter-lungs, we're going to use these T-pieces. Now these T-pieces are designed as a water trap. What happens, if I take the top off, you can see, you wouldn't normally take the top off in normal use, but you can see what happens. As I exhale gas into this side, that gas cannot pass, let me see which way is easiest for the camera, probably that way, that gas cannot pass through to the other side. Its direct path is the water's going to go in and come down here. So any moisture or water is going to go down and into the counter-lung first. For the water to come back through the inhale side, what needs to happen is the gas needs to go up and over this little tube. So when I inhale, I'm going to suck gas from the counter-lung up here, up over the top of that lip, and then down, it's right there, down there and out this way. So the gas has to go down into the counter-lung, then up, over and back through. That's the only way that gas can pass. It means that water is very unlikely to pass from the exhale side into the scrubber at the back. So built-in design there. Got an O-ring on the top, we'll just check that that's in place because we've taken it apart. We want to inspect these for cracks, any damage to the threads. As you can see, these are just a thermoform piece of plastic, so they're super cheap. If you break one, you just buy another. So they're a nice bit of nice bit of engineering, super solid. If you break one, not really a problem. On the base, we've got a little anti-collapse device that stops the counter-lung bag from sticking against the hole and not being able to inhale or exhale from it. So this is our anti-collapse device. So we need to make sure the anti-collapse device is in place. We have an O-ring here on the base. I'm going to remove the O-ring. Just make sure it's clean, in good condition. I can then pop the O-ring back in place. So we have one side with the thread on it. We check the thread. The other side with the thread on it. And then we have a thread with our anti-collapse device on the bottom. I'm going to insert them into the counter-lung. So it tells me on my checklist, once you've inspected both T-pieces, which we have two of those, attach T-piece to the exhale counter-lung with the water trap facing down. So our exhale counter-lung is the counter-lung with this device. This is a dry soothe dump valve. Okay, on the rebreather this is called our OPV or overpressurization valve. If the counter-lung pressure was to build up too much, rather than damage your lungs, the gas will pass out through this valve here. During an ascent where the loop is closed and I'm on bailout and I'm extending, I can open this, make it very easy for that expanding gas in the rebreather to leave automatically through the overpressure valve. So this is our exhale one. We call it exhale because what I can do if I want is as I'm exhaling and spit moisture and water are going into this counter-lung and slowly filling it up, I can then also open this and squeeze the counter-lung and dump out any moisture or water that's in the counter-lung. That's why I don't want to get them the wrong way around. It wouldn't matter if I got the counter-lungs the wrong way around for the breathing effect of the rebreather. It's just that water trap would be difficult to use. So to put the T-piece in, I push out the base of the counter-lung to make sure I've got a nice clear access point. Just check inside with my finger again. Inspect it, smell it, make sure it's nice and clean. There's a nice smell of mould. Make sure the thread is in good condition. Again, really nice feature about this rebreather. Should this thread in here be damaged, a counter-lung is going to be quite an expensive component to change. However, with the Poseidon rebreather, we just remove this locking ring, and then I can remove the threaded section itself. Okay, so all the threaded sections on this rebreather, because they're plastic on plastic, and potentially you could cross-thread it or strip it, you can just buy a new one at a very cheap price and replace that part alone without having to replace, huge components of the rebreather that were manufactured as one. So quite a nice idea. Then put the locking ring up, just hold that in place. Again, this is not part of the stand-up build-up process, just to show you guys. I'm going to fit the T-piece. I'm going to screw it in to the bag. As I screw it into the bag, I'm not going to over-tighten this. Remember, it is plastic on plastic. I'm going to get to the point where it stops. I'm not going to over-tighten it. I need to make sure that the water trap, so which is where the water can go in and down, is facing downwards. So tilt it back a little bit. It can actually go back 4 or 5 turns and still be on the O-ring. So it doesn't matter that I've come back off where tight is. At that position there, the water can now enter and it will go down into the counter lung. Before I inhale, it's then got to go up and over. So this T-piece on my right hand side, which is my exhale side, the water's going to go down and into the counter lung first. So that one is set up correct. The next one is our inhale counter lung. Our inhale counter lung is going to be sitting on top of our left shoulder, and the inhale counter lung is exactly the same, except for here is a blanking port. This is for an accessory later. For what we're doing now, it doesn't do anything, it's just a blanking port. It makes it easy to decide that this is our left side. Again, we open up the counter lung, same thing, check inside, smell, make sure it's clean. Then we're going to input our T-piece, but this time we put the water trap facing the other way. So this way, stopped, and now the water trap's facing that way, which is the wrong way. So I'm going to give it a 180-degree turn and make sure that the water trap is going this way. And this way, that any moisture or water that's generated by the scrubber itself, if it does come back up, because you're somehow upside down, which is not advisable anyway, but if you're somehow upside down, the water will pass, hit this water trap and go down into this counter lung and sit in this bag before you inhale it. So again, you're not going to get any water into your mouth. There's very little water in this hose here. So it doesn't matter that you can't clear it because it's our inhale side. If we breathe in, it'll come through the flapper valves anyway, through the mushroom valves anyway, and be passed to our exhale side. We'll drop into our exhale counter lung where we can get rid of it. So we make sure that this one is in that direction. When you hold it on your body, it's easy to think about it like this. Gas is going from our mouth in this direction, so we can put our thumb into the right hand side, and then it comes down and then it goes in through this one, so I can put my finger in this side. My thumb won't go in there because I hit the stop, but it will go all the way in there, you see. So then I've got an idea that I've got the T-pieces the right way around. It's not critical to the rebreather. The rebreather will still keep you alive. It will still do all of its functionality with the T-pieces the wrong way around. It's just if you get any moisture trapped, it's a lot harder to get rid of. So to make it as easy as possible, you put it facing in this direction. Now again, these are interchangeable. You can put them from side to side and it won't make any difference. Again, just to make this rebreather assembly as simple and as trouble-free as possible. So I'm going to tick that off on our checklist. Connect the counter lungs to the unit, exhale on the right and inhale on the left as warned. So I'm going to connect that one there. I want to make sure that again, put my breathing hose in place. On that side, and then I'm going to pop on this side, again, pop it in place. The back of these counter lungs have got Velcro on that allow them to just Velcro onto your harness. That makes it super easy for the cleaning process later. You just unvelcro the counter lung. What I'm going to show you now, this is one of the technical counter lungs or tech counter lungs, and you notice that it's quite a bit bigger in size. It's got a bigger volume. It's also got space to add these manual addition valves. So should the rebreather not do what it wants it to do, or you want to change something on the rebreather's loop manually, you would manually add oxygen via this valve. And it's basically a dry suit inflator valve, as you can see. Pop the gas on there, and then I would be able to inject it manually, and that would inject gas into the rebreather. Still got an OPV on it, the same as the other XL counter lung, a little bit bigger. Again, you can see that the Velcro's on the back, and the clips allow me to attach it to my harness or my wing. So quite a nice set of big tech counter lungs. But if you only do recreational diving, no need for the bigger, slightly more expensive tech counter lungs. The recreational counter lungs are suitable. So connect those. Connect those. Okay. The next step we're going to do is to connect the breathing hoses, the front breathing hoses, to the T-pieces. These are the front breathing hoses that we've already specified, and again, I can either push them in place first and just check the O-rings in, and then tighten the locking ring, or I can put the locking ring directly on to the rebreather like so. Done. My next step is to inspect the electronics module and the two O-rings on it. So I'll take a little bit of time now to explain this electronics module to you. So, a lot like the other rebreathers except the Revo, this is the most expensive bit. It's the head or the electronics or the E module. depending on where you come from. Okay, and what it's got is a couple of different components, which I'll show you now. Let me just move a few of them out of the way. Okay, fantastic. So, this is the base of our E module. The base of our E module here, we've got some gas injection points. We have 3 gas injection points here, and the gas injection point here that fits on top of that round O-ring inside the head. Okay. Here we have our cell face. Okay, so inside there are our 2 oxygen sensors. Our 2 oxygen sensors also have a gas path so that the gas can be ejected directly onto the cell face and make sure that any water is blown off. This machine is quite interesting because it doesn't just have a single solenoid. Most of the rebreathers have a single solenoid. This rebreather actually has 2 oxygen solenoids for metabolism. So when you're breathing normally and you're depleting the oxygen in the loop, you'll get one solenoid fire and then the other solenoid fire and one solenoid fire, then the other solenoid fire in a series of 6 blasts. Those 6 blasts will change in length depending on how much oxygen needs to be added to the rebreather, but it's a very small amount. If one solenoid were to fail, it's great because you've got another backup. It just means that backup one will need to work a little bit harder. So you've got a backup oxygen solenoid built into the rebreather. However, the machine will alarm to tell you that that solenoid is now not drawing enough power or there's something wrong with that solenoid. So you're going to, and it could be that the machine oxygen isn't rising as fast as it imagined it should do, and you'll get a warning telling you to bail out. Because we don't want you on the recreational mode to be diving with anything broken. But you've got a spare just in case you do stay on the rebreather. The other 2 solenoids, one is an oxygen calibration solenoid that we use to calibrate the rebreather with oxygen. That either the surface calibration or something called the hyperoxic linearity check, which I'll talk about a little bit later, or the diluent calibration solenoid. So like I said, every 5 minutes it's going to put diluent directly onto the cell face. That diluent calibration solenoid, oxygen calibration solenoid are also built into this head. So 4 solenoids in the top of this head. They are all located underneath this part here, which you can see is called the gas block. We have diluent and oxygen fed from the first stages at low pressure into the gas block and then distributed by those 4 solenoids. This is the Se7en rebreather, and you can tell it's the Se7en rebreather because of these 4 sub-connectors. These are wet connectors, and they screw in like such. Okay, so this means that if you were to damage a part of your rebreather, let's say the hood or the handset, you could just remove it from the head and put it again somewhere else. It also means that the rebreather uses a CAN bus system. You can plug any one of these into different ports and it'll still do the same thing. One of the first rebreathers to use a bus system was the Poseidon 7. We've got a lot though. As you can see, we've got quite a lot of port cables coming out. Most rebreathers tend to have 2, one for the primary monitor, one for the backup monitor. So what do all these cables do? The first cable is the one that goes to our handset. And this is set up in recreational mode, so this is the recreational paddle. The paddle is a very big LCD display and it's got all the information the diver needs in this little window. Gas consumption, gas amounts, ascent rate, partial pressure, alarm windows, and then information screen that tells you your depth and your no decompression time, and the temperature and a few other little bits and pieces in the information window. This paddle sits on your arm. It's quite big, but it's very, very simple to see. From even the other side of the dive, I can keep an eye on my buddy and make sure that what his PO2 is just by being on the right side of him. So really, really big display. You'll notice though, there's no buttons on this display. There's no way for me to interface with the rebreather underwater. I don't need to press any buttons to change anything. It's completely automatic. The only way I can input with this rebreather is via these 2 wet contacts. On the surface, if I was to lick 2 fingers and touch these 2 wet contacts, I would activate the rebreather should the battery be in. Underwater, these 2 wet contacts won't do anything because of course they'll be wet. It also detects then if you fell into the water. If you fell into the water and these wet contacts were to get wet, the machine would automatically start up and do its best to keep you alive. Of course, it can't turn the cylinder valves on, so your gas would have to be on, but it would do its best to try and keep you alive should you fall in the water. That's on one side. On the other side, we have a wire that comes to our mouthpiece, and that's connected to our head-up display. Our head-up display sits in front of your eyes, and in the Se7en, it's got 2 lights, a red light and a pulsating green light. Flashing red is not good. Green pulsing is good. So quite simple to understand. If you're seeing green, everything's great. If you're not seeing green or you're seeing red, then there's a problem. So up on the mouthpiece. The other really nice thing about the hood is it's got the Hammerhead Diva vibrator built into it. So that means that in the likely event of an emergency, not only will the hood flash red, it will vibrate the mouthpiece in your mouth to let you know tactilely that you've got an alarm. So we've got a tactile alarm function on this rebreather as well. I'll come to the mouthpiece a little bit later on. The other two cables that we have are these two cables here. And these two cables connect to our first stagers on the high pressure port. This is our gas monitoring high pressure system. So rather than having SPGs with long hoses on, we've got these very short amount of gas inside this little connector here that's then read by a digital sensor. It sends that signal to the electronics. So the machine can tell, using the electronics, how much gas you've got. So a lot like a transmitter, but it's hardwired. Now, being able to tell how much gas you've got means that this rebreather can do a clever calculation. It can calculate, based on the current depth, how long your gas supply is going to use based on current consumption. It can also calculate, if you were to bail out at this point now, do you have enough gas on board to be able to make it to the surface via the onboard bailout valve? So it's constantly running calculations in the background because it knows how much gas you've got. Also, if your gas supplies were to get low, it would start to warn you. It would first give you a soft warning that your gas supply is getting low. If your gas supply got critically low, it would start giving you a hard warning, beeping, vibrating, and flashing constantly. And I have to promise you, it's very hard to ignore. So the idea of this rebreather has got a bunch of systems that work linearly to make sure that you're going to be as safe as possible. So those high pressure sensors are a really nice idea. They mean you don't have to have less hoses, you have less failure points, and the gas can be monitored by the electronics. On top of the head, if we look in a bit more detail, we've got our battery hole, a battery module. Inside the battery module there, we slide the battery in. There's 4 contacts on the bottom of the battery. Those 4 contacts, unfortunately, are a bit exposed to water. When you take the battery in and out, water goes in onto those contacts. And if you're not careful, these contacts can start to corrode. One of the problems we see from time to time with a rebreather that's not very well looked after is those contacts will corrode, and the contacts then on the battery will corrode. Either is designed. I could get the battery wet, or I could get those contacts wet, and nothing would happen. The problem comes when either is wet and I put them together. Now I have electricity flowing through that water, that causes the electrolysis, and that damages the pins. That means that now you've got a slightly smaller pin than the hole it's fitted into in the battery, and you're going to get connectivity issues, and that's not great. It's a maintenance problem, honestly, but as a rebreather that was designed to be completely foolproof, if you're not careful and you don't look after that little part, it can be a little bit of an issue. As you can see on the battery, we've got quite small pin connectors. So 4 pin connectors on the battery, aligned with the 4 pin connectors in the battery hole. This battery, as you can see, is the smart battery. The smart battery itself has got a battery built in there, but it's also got a circuit board, a computer in there, and the electronic buzzer. So in the event of emergency, this will beep, and it's quite loud. You'll hear it when we do our startup test, and it's right behind the diver. On the back, there's an LED as well, a bright red LED. So if the diver is in an emergency situation or needs attention, then this will flash red really bright from the back of the diver. That alerts his teammates to the fact that he's got a problem. So not only will they be flashing in front of the diver on the hood, the handset itself will be flashing, the whole back of the rebreather will be flashing red to let them know there's a problem at all. There's no normal state. Normal state is off, so there's no green light in the back, but just a red light to let you know that your buddy's got a problem. Got a computer built in here. The nice thing about this machine is there's more than one computer. So in the electronics, there's a computer. In the handset, there's a computer. In the battery, there's a computer. In the hood, there's a small computer. All of those computers need to be on the same firmware. They need to be talking to each other properly for the system to work. And each one controls its own part of the rebreather. So a little bit like the Revo, the electronics are kind of spread out over various parts, and each part does its own thing. This battery in the Se7 also has the Bluetooth module built into it as well. So if you change the batteries, you need to make sure that you get the right battery for what you're doing. So this is the deep battery, and it fits into the base of the rebreather. We'll take a look now at the mouthpiece. Okay, so this is our mouthpiece. This is called the Gen 7 mouthpiece. This is this is the older mouthpiece actually. This is the Mark 6 mouthpiece. The newer mouthpiece has dark colour here. The mouthpiece itself is really nice because it's the lightest weight BOV on the market. It's one of the smallest, most compact BOVs in the market as well. So really, really simple. You can see that weighs pretty much next to nothing. built in between open circuit now and rebreather mode. Where you look at the other rebreathers that we've had over the past few weeks, we just have what we call a DSV, a dive surface valve. It's either in dive or it's in surface. There's nothing in between. In this rebreather, we've got closed circuit mode. If we flick this switch up, and so it's in front of your eye, this is closed circuit, and if we flick it down, now it's in open circuit mode. Open circuit mode is this hose is connected to essentially a Poseidon Extreme regulator. It's got a slight modification, but generally it's the Poseidon Extreme regulator, which is a 200 meter rated regulator, so a high quality regulator, with the purge valve here on the end and the exhale ports here on the front. So that in an emergency, if you were to be in the closed circuit position and have a problem with your rebreather, all you would need to do would be to push the lever into the forward position, and you would be breathing from the diluent tank, from the 3 litre diluent tank. Okay, the machine has already been calculating, did you have enough diluent to bail out? If you didn't, as soon as you start to get close to that limit, it would ask you to move up to make sure that you did have enough diluent to bail out. So in this mode, in the recreational mode, the onboard bailout is a very good way of getting you off the rebreather in an emergency onto a fresh gas supply. You don't need to find an offboard regulator. You don't need to deploy much of a skill set. All you need to do is move that switch from that position to that position, and you can start your ascent and get home. Now, 3 litres, as I'm sure you guys are aware, at 40 metres probably isn't a lot of gas, especially if you're breathing heavy because you're hypercapnic, especially if you're panicking a little bit, and especially if you make a slow ascent. So we don't really recommend diving deeper than 18 metres with onboard bailout only. Okay, as soon as you go deeper than 18 metres, you really want an offboard. Ideally, all scenarios, try to take a bailout with you anyway. 3 litre, not ideal for any kind of diving, but because this machine's designed and built like that, and it's got a calculation running that you've got enough gas in the background, you are capable of doing it. Okay, so it is designed like that. And that's why with this rebreather, I don't actually mind having a BOV. Okay, the BOV itself is really, you know, a high quality regulator, and it gives a lot of gas, and it's as easy as breathing from a normal regulator. It's not really compromised in its design at all. So it's a fantastic BOV. Lots of people have had adapters made and put this onto JJs or put this onto other rebreathers as well because of how fantastic the BOV is. However, my personal opinion, as I'm sure we've already discussed, is not to modify a rebreather from the manufacturer standard specification. You know, I don't mind if you change your backplate or harness or something, but generally, especially the breathing loop, I wouldn't modify it from the manufacturer's design at all. Also, there's some complication, which is a topic for another day, about bailing out onto an onboard valve at depth. Okay, if you're at great depth, that 3 litre supply is going to be almost useless to you, maybe just a couple of breaths, and then you're going to need to get off it. And that might not be possible. If you want to use an offboard gas connection system where you plug in other offboard gases, that's also an option, but generally it's compromised. Your best bet is to go to a normal regulator as soon as possible. So for the slightly deeper diving, we teach you to bail out directly onto your offboard gas and make that big volume with a really high quality regulator available for your bailout. Whereas the bailout valve for the recreational stuff is a fantastic idea. So mushroom valves, as we've seen before with all rebreathers, they're built here into the mouthpiece. They're just removable. They're a very soft, very flexible membrane that allows us to move the gas in different directions. They're built here into the mouthpiece. Okay. Of course, like all other rebreathers, I need to check they're in good condition, and I'll do a test on those when we get to it on our checklist. Very important, again, make sure that our mouthpiece is in good condition. This isn't the standard mouthpiece, actually. This shouldn't be on here. This is should be removed and replaced with the Poseidon proper mouthpiece that's a bit wider and allows better gas flow. Okay. So just make sure that we check now our 2 O-rings. So on the base of the O-ring, on the base of the rebreather on the head, we've got 2 O-rings. They're slightly different sizes. They're actually round O-rings, but they sit into a square groove, so it kind of makes them square. We just make sure it's clean. The O-rings are nice and greased and nice and smooth, because this electronics module is now going to fit into the top of our rebreather. So they are clean. Inspect the O-rings, fit the E-module firmly, and you should feel 2 bumps as it goes over the O-ring. So just place everything into place. What I'm going to do now is tilt the electronics module, place it into the top of the rebreather. With a little bit of light pressure, those 2 O-rings will go bump bump as they fit. There we go, there's my bump bump. Okay, while I'm at it, it asks me to finger tighten the 2 electronic module bolts. So either side there's 2 bolts. I'm just going to finger tighten those. And again, they aren't there for any reason. There's no positive pressure generally inside the rebreather. The rebreather internally should be pretty much ambient. So it won't blow itself out, those O-rings will hold it in. But should somebody pull on the cables or you catch and snag them on a wreck or something, you just want to make sure that the E-module can't pop out and flood the rebreather. So we've got 2 little bolts that just kind of hold it in place. And they only need to be finger tight as well. The next step is to secure the oxygen and diluent first stages. Nice and simple job. Just make sure that our hose routing is as we would like it. The diluent side goes on one side, like that. And these are the Poseidon Extreme first stages. So these are 200 meter rated, again, Norsoc standard first stages. Really high quality design, much higher interstage pressure than a normal regulator. Well, not much higher, normally 12 bar. The oxygen is a reduced in-stage pressure again, just like all rebreathers, to allow the solenoid to use less gas and to stop it sticking shut. The in-stage pressure on the oxygen is lower. So we're going to pop that into place like so. Just make sure that our hoses are nice and neat and not crinked. That's going to go there. That's going to go there. Put the oxygen first stage into place like so. Just tighten it up. Now, having the first stages and the valves up above my head is going to help me achieve better trim in the water. With the rebreather with a shoulder mounted counterlong, you imagine you've got a bubble of air right up at the top of your body. If you combine it with slightly heavy feet, you're going to naturally go out of trim. If you've got a rebreather with all the valves and all the heavy first stages at the base, it means that that's also going to affect your trim in a negative way. So by moving all of that up into the top of the rebreather for a recreational diver, it means that it's going to push them forward. And then that kind of offsets the example of, you know, needing to be able to shut down. In a recreational rebreather, there shouldn't be really any need to shut down the supply. If the rebreather's doing something it shouldn't do, you just bail out. So you go into the open circuit position, so it wouldn't matter what the rebreather did and you'd have no reason to shut it down. That means that we've got this like slightly better trim as a standard on the rebreather. Okay, a couple of questions here. Let's have a look what we've got. The battery controls, yeah, it does. Why do you need a larger counter-lung volume for technical diving? That was just to make sure that the work of breathing was in standard. So as you went deeper, the gas that was moving around the rebreather would needed to be a slightly bigger volume. Potentially there might be more chance where you're breathing a little bit heavier when you're working a bit harder, so they kind of give you a little bit more gas volume. Yes, Jens, this will be available later, just in our live video section, so if you go to the Facebook and go to the live. I think that's it for questions for now. Other than that, you guys can ask us any more questions as we go through. We've got our first stages, oxygen fitted, diluent fitted. I'll now connect the low pressure inflator to the wing, which we don't have. Okay, next step is to check the mouthpiece mushroom valves in the closed circuit position. To do that, as before, I'm going to make sure that I'm in rebreather mode, and I need to block one side. Remember, we inhale from the left and exhale to the right. So if I block my inhale, I should not be able to inhale, but I should be able to exhale. So I'll just block it with my palm. Exhale, yes, inhale. And no, I can't inhale. That means that this mushroom valve is doing its job. I'm then going to cover the exhale. Now I should be able to inhale, but I shouldn't be able to exhale. And I don't need to do that excessively difficult. Try to get in the good habit of making sure that the mouthpiece is in the open circuit position when it's not in your mouth. We're happy with the mushroom valves. Verify the gas flow direction. So I'm making sure that even though they both did what they're supposed to do, I'm just going to check. Inhale from the left, exhale to the right. That's what I'm after. Perfect. It should exhale towards the diver's right shoulder. Yes, it does. Attach the mouthpiece to the front breathing hoses. I'm going to lift the hoses up, just bring them to the mouthpiece, attach it like so. Now, what you can see with this rebreather is that the mouthpiece, the hoses, point in a downward direction. So they come down, not like all other rebreathers where they go horizontally. Horizontally, they kind of then go up, and if you twist your head, you can sometimes see them. By having the loop hoses go in a downward position, it means it's much easier to see what's going off. A lot of people claim on this rebreather it's even difficult when there's no alarm to see the hood, because the mouthpiece is downwards in this position, out the way, so it feels much freer. Some of the other rebreathers, especially with big breathing hoses, sitting in front of your face, and coming in this direction, when you start to move, you can notice them. But these go into a downward position towards your shoulders. So it kind of makes the life a little bit more open. Okay, I'm just going to route this handset over to the correct side, which is over here. Now, the next step is to do a negative test on the rebreather. I need to make sure, as it says, ensure the overpressurization valve is closed to the right and perform a negative test on the rebreather. So what I'm going to do, like the other rebreathers, I'm going to evacuate with my lungs all the gas out of the rebreather, exhale through my nose, inhale through my mouth, exhale through my nose, and suck the loop volume until it's completely gone. This is going to make sure that any O-rings that I've got in here are all nice and sealed, and any parts of our collapsible system collapse and don't let any gas in. Let's do that. I need to put the mouthpiece into closed circuit position. And you can see that the mouthpiece has collapsed all the breathing hoses up nice and tight. By collapsing all those breathing hoses nice and tight, I've made sure that there's a vacuum inside the rebreather. I'm going to check that vacuum in a minute or so's time, maybe 1 minute, 2 minutes, and just check that that vacuum remains. I can feel my counseling bags have completely collapsed. If they were to start to come back to their shape again, it means that we've got a leak inside the rebreather. Why check the direction of the bulb? Would it be upside down? No, great. If you were to accidentally put the mushroom valves in upside down, sorry, the wrong side, it means that the gas could go in the wrong direction. You'd figure that out in another way as well, because it's mechanically interlocked so that I can't screw the hose in. If the mushroom valve carrier is in the wrong side, I can't physically screw the hoses on, but it's a good idea to check before you get to that problem. What bit of the Poseidon do you dislike? I dislike some of the plasticky parts, to be honest with you. I think some of those could be made out of slightly higher quality material, but I know that that would have an impact on cost, so I'm prepared to accept it. Another thing that I was not so keen on was the upgrade path, the way it was launched. Not so much the fact that it's got an upgrade path, the fact that you would spend a bunch of money on a rebreather and you get a load of customers built on that level, and then they would release an upgrade that was quite expensive and you would move to the next level. And you think, okay, now I'm finished. And then another upgrade would come. And so you'd upgrade and upgrade and upgrade. So that kind of put a little bit of sour taste in people's mouths. Generally, I really like the rebreather. The front-mounted counter-lungs are not very nice. There are a back-mounted counter-lung set, but once you've got used to front-mounted counter-lungs, the breathing is great. It's just that fact that you can't kind of reach across to maybe do your dry suit dump. You can't really reach across to get to underneath your arm and clip your stages on and stuff like that. So the front-mounted counter-lung set isn't ideal. The back-mounted counter-lung set is much nicer. It's the same counter-lungs, they're just flipped around basically with a pad in the middle to keep them together. But the front-mounted counter-lungs is something I'm not fantastic about. What bit of it would you like to see on another rebreather? The cell validation algorithm is fantastic. I know it's patented by Poseidon, so that would be a really nice thing. If we had the ability to inject oxygen directly at the cell face, potentially on the other rebreathers you'd want to do that a manual process where you press a button to make it happen, and you could confirm the calibration of the cells during the dive. That would be a nice function. The other nice function this rebreather does is something called a hyperoxic linearity check. When we calibrate ourselves on the surface, we calibrate with either air or oxygen or both, and it draws a line, and it assumes that if this is air and this is oxygen, it draws a line and it extrapolates what more than oxygen would be. So a PO2 of 1 is here and a PO2 of 0.21 is here. A PO2 of 1.3 must be right here. And that's a guess. Okay. If your cells are starting to fade towards the top end, it might not reach that. Okay. So this machine does something called a hyperoxic linearity check. During descent, during your initial descent, the first descent you make, when you arrive at 6 meters, you'll hear the machine fire the oxygen calibration solenoid. So you'll hear pshh. It's a very, very short space of time. And what it's doing is it's putting pure oxygen on the cell at 6 meters. So right at the cell face, pure oxygen at depth of 6 meters. What happens then is if the machine can read 1.6 or the value it's looking for, it's not actually exactly 1.6, but if it can see that higher value, it then can draw another line to make sure that your cells can be linear from 0.21 all the way up to 1.6-ish. So that way we can guarantee that cells aren't current limited. If the machine fails It doesn't alarm and bail you out. It just stops the PO2 of the dive rising any higher than 1. Because we knew on the surface we can calibrate to 1, we can dive at PO2 of 1. It means our decompression time is going to be less, and it means that our decompression that we do would be longer, but it's not a massive factor. You just need to consider the narcosis side of it, which is something that's slightly a bit different. But if you're in the recreational range, that wouldn't be a problem for you. So the machine would limit you to a safe way. Another thing that I really like about this rebreather is the way that it gradually increases the set point. On most rebreathers, you will, during your descent, at some point, decide to turn from the low set point to the higher set point. If you're on the higher set point for descent, you'd find the oxygen would spike during descent. If you make sure that that set point comes up gradually, which is what this rebreather does, then you can figure out that you arrive at depth on the right set point without ever having any spikes, even for fast descents. The same thing during ascent. The machine notices that you're moving up through the water column and says, well, he's moving up, so he wants to start to get out the water. So in the recreational mode, it can start to drop the set point. And that means that it's not adding so much oxygen during your ascent, where you're having to vent the loop anyway. And so it makes your buoyancy easier during ascents, because it's not adding so much, it's just dropping the PO2 off in the set point. So that's a fantastic thing that it does. It's got a whole array of sensors inside here. One of the sensors that they tried to figure out was it's got an axis yaw sensor in it. And they were trying to figure out that if the divers dip slightly, does that mean they're going to descend? And if they're going to descend, we won't inject oxygen. And the machine's got so many clever sensors inside it, and it's doing such complicated processing that it can really be a step ahead of you. For a diver that's struggling with their buoyancy in shallow water, keeps going up and down, it will reduce the set point, provided that diver is in decompression. It says he's not in decompression, so he doesn't need so much oxygen. If I gave him less oxygen, it'll make his diving easier. So the machine can correct, let's say, not poor skill, but it can help you develop the skill faster because it's not adding gas in such a fast way. So it means that the machine's a little bit easier to dive with. Lucas, do the back-mounted lungs well? The back-mounted lungs do work okay. They're a little bit tricky to get to because they're a bit of a compromised design. The front-mounted lungs designed to go on the back. That was to keep the cost down. So the cost, is one application, but the other one is, they work nicely as long as they're set up well. So that kind of figures with all equipment. But the Poseidon ones in particular, you need to make sure you get them really set well for them to feel as good as their front-mounted counter lungs. So, where do we get to on our little list? So we've done our negative test for a minute or so. We're going to open this, and you see everything jump back. This held a really strong negative test, which it should do because it's just been calibrated. Now, we're going to do a return the mouthpiece to the open circuit position so that no gas enters, and now we can start the machine up. There's two ways to start the machine up. I can either put the battery in or start it with the wet contacts. To do this, I'm going to move the machine a little bit closer just so you guys can see the startup process. Tony says she doesn't understand the difference between the linearity check. So what's the difference between your machine and this? Basically, on your machine, Tony, which is the Red Bear, the VMS Red Bear, when you descend, you're going to naturally increase your PO2 up to maybe 1.3. But you are not confident. Well, at least you can be confident, but you're not 100% sure that those cells can read anything above 1, which is what you calibrated. The only way you're going to know that is by manually adding oxygen and seeing if the PO2 goes above 1. And if it starts to go above 1, it will do. If you're running completely electronically, so you're not manually adding any gas, the machine cells could be limited, so they can't read any higher than a PO2 of 1. However, the set point might be telling them to go above 1. So that means it will keep injecting oxygen. And it'll keep injecting oxygen until the cells do reach 1.3 or whatever the set point is. If they're incapable, it will keep adding pure oxygen forever. And that means that you could be at depth with the machine just adding pure oxygen until the loop becomes almost 100% oxygen at whatever depth you're at. So you could become hyperoxic, too much oxygen in the loop. And you wouldn't notice, except for the fact, that you'll hear the solenoid firing and stuff like that. So on another rebreather, you can do a manual hyperoxic linearity check, which is where you stop at 6 meters. You're going to boost the PO2 slightly to see it peak above 1 to a level where you would suspect it. But you're at a depth where even if you go to pure oxygen, it's not going to be a problem for you physiologically as a diver. Some divers elect to do a hyperoxic linearity check at the beginning of the dive if they're going to do it manually, and some divers elect to do a hyperoxic linearity check at the end of a dive. Depends on what your thinking is. High oxygen then suddenly descending isn't great because you're going to spike the oxygen. At the very end of the dive, you confirm the cells are okay, ready for the next dive probably, but you haven't really checked them for that dive. So there's a bit of an argument between the two. Again, conversation for another day, but the difference between your rebreather, Tony, and this rebreather is your rebreather doesn't do an automatic hyperoxic linearity check. It's something you would need to do manually, and this rebreather does it automatically during descent, and if it fails, it limits the maximum set point. Yeah, hence your 6 metre check for 1.2. Yeah, so as you were taught, you do a check manually to make sure your cells can read above. This machine does that all automatically. Right, let's bring the machine a little bit closer. As you can see, it's super light. Don't need to worry too much about the weight. Okay. Hopefully you guys can all see the paddle here. I'm going to try and mount it in a position where it's easy to see. Might use these bits of bungee to hold it in place. Okay, how's that look? Great, you guys can see that there. All right, so we're going to start the machine up. How do you manually add air and dump on the back mounted counterlungs? The back mounted counterlungs have a pull dump that's on the right hand side, so you can pull dump just like on the JJ. And the manual additions, they're added on top of the T-pieces. So it's got two inflator valves that are fitted right here on top of the T-pieces. So you press down on top of the T-pieces manually and it'll add gas. As an example, would the cells be limited on the fact that they're old? Yes. So basically, without going into too much detail and taking too much away from the course, the way the cell works, it's got cathode and an anode, and they create a voltage when oxygen is added through the electrolyte. So oxygen comes into the cell and a voltage is created between the cathode and the anode. Now, over time, the parts get eaten up, okay, so they can't produce as high a voltage. And that would mean that the cell might be something called current limited. So it could generate the lower voltages, which would allow it to calibrate, but it couldn't generate the higher voltages, which are the higher PO2s. And that happens either over time or through damage to the cell itself. So it's not just a case that they're old. It might be a case that they've been badly looked after. A temperature would affect it, the amount of oxygen they're exposed to will affect it, and any potential damage to the anode or the cathode may also affect the voltage that it can produce. Same thing with the actual pins on the cells themselves. If they start to fade, you might not get the same voltage output. Okay, so we're in place. We need to get our smart battery. We've got a smart battery. And there's two ways to start this rebreather. If the battery was already in, I would need to use my wet contacts. Because the battery's not in, I'm going to use inserting the battery method. So it says dropping it. Pop that into place. Just on my checklist. Insert the battery or start the unit via the wet contacts. And complete the checks specified by the handset. So when I insert this battery, we're going to go quite quickly because this machine is going to do 54 automatic self-tests. The first bunch of tests all the way up to about 14, 15 are internal computer tests. So they're RAM, ROM, EEPROM tests. They're making sure the computers can all talk to each other. They're making sure the solenoids draw enough power. So they're all internal checks. Then you're going to see a few checks happen. You're going to see the backlight light up to check that the backlight works. You'll see the light at the back of the rebreather light up. The handset, sorry, the hood will light up red, the hood will light up green, and it will test the buzzer. What it's doing is it's putting power to all of these components and checking that the voltage draw is right to assume that they're working. So it goes through and checks every part of the rebreather. It'll then ask us to manually step in from time to time. You'll hear it beep and say, please step in. It might ask me to open the cylinder valves, to change the mouthpiece position, and it's going to go through its startup check. One of those checks is to calibrate, and during its calibration process, it'll also confirm that I've got the gases that I said I'd have. So, 54 tests. On the one side here, you'll see the test number. If it fails, over on the other side, you'll see the failure number. So we've got an idea where we are. Let's start the machine and we'll see how we go. So in goes the battery. You'll notice the first thing it will do will be a screen test. So now it's turned the display on and we've test 10 already. So it's done a whole bunch of tests already. We can see our battery voltage at the bottom and we can see our little bubble man. That's our no dive man. So it's a little face with bubbles saying don't breathe from the rebreather. We're at test 16 and things will start to light up now. So if we're going to look at the hood, there's the backlight, and then on the hood, hopefully it's not too bright, you'll see it. We'll get some lights on the hood in a minute. So that's the backlight test, test 17, test 18, red on the hood, look, green on the hood now, red on the back, you see my hand through the back there. Then, in a minute, the hood's going to vibrate, you might be able to hear it. And now, beep, beep, beep. That's our alarm, checking our alarm's working at the back, and the machine's asking us to do something. What's it asking me to do? It's very simple, I can see it here on my display, it's saying CC. Please go to closed circuit mode. So it's asking me to go to closed circuit mode. So I'm going to move this mouthpiece from this position to this position. What it's doing here is it's making sure that there's no volume inside the loop. A little bit later on it's going to inject gas. If there was no scrubber inside the machine, the amount of gas that it would see when it injects would be greater. So it can detect a little bit whether there's a scrubber installed or not. It's not a perfect system, I'll be honest with you. But it is a way of checking. We've also got a manual here, look. CANISTER. It's reminding me, have I fitted a canister of softener lime inside, or is there time remaining? I need to manually lick my fingers and touch the 2 wet contacts. If I touch those 2 wet contacts, I've confirmed that there is definitely a scrubber in here. So I'm going to touch those 2 wet contacts right now. It's going to log that into its like black box data recorder for later on. You can see the progress of my touching the contacts is complete. Now we're on test 43. Test 43, it's asking me to go to open circuit. I'm going to move the machine to open circuit because it's going to do its next test. And its next test is a positive test. You'll notice when I did my negative, I didn't do a manual positive. I didn't blow the rebreather up and check it. It's going to do that itself. And it does it in 2 ways. First thing it's going to do is it's going to inject oxygen to a low pressure. And then it's going to see if that low pressure stays. It's using the 2 metabolic solenoids to inject oxygen. If they then shut and the pressure does not rise using a very sensitive sensor inside, it knows that those solenoids shut correctly and the solenoids are not in a stuck open position. That's an automatic feature. It'll then inject oxygen again to blow the rebreather to an even higher pressure and do our actual positive test. Okay, so I move my mouthpiece to the open circuit position, and as you can see, the machine detects that automatically. I don't have to tell it by a set of buttons. I've moved from open circuit to closed circuit. It knows by the switch on the mouthpiece whether I'm in open circuit or closed circuit. Test 44, and you can see it on the screen, this machine is very intuitive. If it's flashing, that's what it wants you to do. So at the moment it's flashing oxygen down one side and diluent down the other side. So it's asking me to turn the gas on. I'm going to turn on the oxygen, again, nice and slowly. And you'll see the oxygen pressure will rise. And then I'm going to turn on the diluent. Because it's a Poseidon regulator, expect it to make a noise. That's a downstream regulator filling up. Upstream regulator, sorry, filling up. And I open both tank valves all the way. Now you can see the machine injecting. It's injecting and blowing itself up to that low pressure, and then it's going to stop the 2 solenoids. Those 2 solenoids are going to stop. When it's stopped, it's going to check and level off. If that pressure remains constant, we know for sure that our solenoids aren't leaking. So we just wait. If I was to compress the counternozzle or squash the rebreather now, it would fail this test because I'm increasing the pressure inside the loop, and it would detect that the solenoid's failed. Now it's going to blow itself up again and monitor the pressure for any pressure drop. Because it's blowing itself up to high pressure, if there's a small leak in the counternozzle and it starts to leak out, it would notice that as a pressure drop, and then it would fail based on its positive pressure test. Again, if I was to press the rebreather here, the machine would fail. Now that's okay in this nice environment. If I'm doing this on the way out to a dive site on a bumpy rib, then I could potentially have a bit of an issue with this test. Hopefully I've done it before I've got in the rib, but you want to make sure the machine is ready to go when you get there. If it was damaged during the process, that's not ideal. So next step, now it's past that test, we're on to test number 50, and test number 50 is asking me to go to closed circuit. It's asking me to go to closed circuit, like the other rebreathers, so that oxygen, as it's injected for the calibration process, can exit the rebreather. If I let the oxygen just build up as pressure, I'm going to get increased oxygen pressure, and I've got a high fraction of oxygen, so I'm going to get an increased partial pressure. So that means the calibration will be wrong. Like the other rebreathers, I could accidentally have it closed and calibrate badly. This machine won't let me calibrate badly because it won't calibrate at all until it knows that the mouthpiece is in the right position. So again, another interlock to keep you safe. I open it, into closed circuit position, it detects that, and test 53, it's going to start to inject gas. First gas it's going to inject is oxygen. It injects oxygen and takes it all the way up to the highest limit. So it waits for those cells to settle with pure oxygen blowing onto them. Once it's got the highest limit, it says, okay, great, that's what oxygen should be. Based on oxygen, I'm now going to inject diluent at a lower limit, and I'm going to check that that is 21. So if that was oxygen and that was 21, are they the difference that I expect to see as well? And so that way it can confirm whether the gas you put inside, the calibration was correct. So you can hear it now injecting plenty of gas to do the high calibration. You'll hear a stop, then you hear another type of noise, and that is the diluent going in. So oxygen was first, now it's adding diluent, and you can see our little progress indicator on the top just letting us know where it is in its tests. So it's injecting gas, and then I just heard psh, which is the one of the oxygen solenoids fire, and that means that this test was passed successfully. And in a second, when it's done its calibration and set all the computers to the oxygen, it's going to say, okay, great. Now test 54, please go to open circuit mode. So again, I go to open circuit. It detects that, and it says B-R-E-A-T-H-E. Breathe. It wants me to test that the bailout valve is working. So I'm going to do a manual test. I need to breathe 1 or 2 bar from the cylinder, so it recognises the high pressure drop, and it'll also recognise that that's working. Test 55 tells me my weeks to service, and test 55 said 105 weeks. So it's got 105 weeks until this machine needs a service again. That was our final test. Now the machine has started up. The machine is now in its dive state, okay? And it says PBR 300. PBR stands for please do a pre-breathe for 300 seconds. So a 5-minute pre-breathe. It's asking you to do that. Above here you can see 0.7. 0.7 is what's inside the rebreather right now. So we're at 1 atmosphere, 0.7, so 70% oxygen inside the rebreather. It'll then flash, say OC, because the mouthpiece is in the open circuit position, and then it flash 0.4. So the set point currently is 0.4. The machine is trying to achieve 0.4, but the actual oxygen inside the rebreather is 0.7. Because the amount of oxygen inside the rebreather is 0.7, it'll just sit there forever. If I was to start breathing and bring that oxygen content down, the machine will get to 0.4. As soon as it drops below, it will manually inject oxygen to keep it up at 0.4. Okay? If I move the mouthpiece into the closed circuit position, what you'll see is that this now will change to CC. It's changed the set point to 0.5 because it thinks I'm going to go dive in. And you hear it inject gas. And I've got CC now, so I'm in closed circuit. Okay? That's really fantastic because I know which position I'm in. If I was to go into the middle here, and not really in any position, you can see that my hood just lit up, and I've got a vibration, and now I've got an alarm. And it says on the mouthpiece, on the handset, MC, no circuit. So that means I'm not in closed circuit, I'm not in open circuit, I'm in the wrong position. So I know that I'm getting an alarm. I'm getting a red flashing light here out the back, and now, because I've left it too long, I'm getting problems. What's happened is I've exposed the loop to air, and so the PO2's come down to 0.21. And now I've got constant beeping, flashing from the handset, from the hood, vibrating, beeping at the back, big red flashing light from my buddy, and it's telling me, bail out, bail out, bail out. So, touch that back to the closed circuit position. The oxygen's come up a little bit inside the rebreather because it was ejecting, and now it's happy again. The pre-breathe timer has dropped down slightly, but you can see here I've got a big number. That big number is the amount of time I can spend underwater. Now, you're used to seeing on your dive computers, I'm sure, the no decompression limit, which is the amount of time you can spend at this current depth based on current factors. It's based on normally nitrogen and helium absorption. This number here is a magic number on the Poseidon. And I don't mean magic in the fact that it does something completely weird. I mean magic in the fact that it takes all of the limits of the rebreather. So this number here will be the amount of time you can spend at this depth based on battery time, how much battery you've got left, based on how much oxygen you've got left, based on oxygen you've got left on your current consumption, how much diluent you've got left. If you've not got enough diluent to bail out, this will come down to 0. As you start to move up, this will then increase again because now you do have enough diluent to bail out. How much oxygen saturations have I got, pulmonary and CNS? If they start to reach the limit, it'll bring this down to give me less dive time. So all the factors, so not only nitrogen and helium, but all the other factors about the rebreather are being monitored into one number. So as a recreational diver, it's simple. I go to depth and I don't let that get to near zero. As soon as that starts to decline to a point where I want to go up, I start moving up. As I start moving up, the consumables inside the rebreather are obviously now going to be there's going to be less of it required. So this number can start to increase again. So I can stay at my new depth for longer. So they're all into one factor here. You can see very easily at a glance your current PO2. You can see very easily at a glance the amount of gas you've got. It doesn't matter in bar. We've just got, this is 100%, which is, you've got all your gas. This is 80%, so you've got 80% of your gas. You don't need to know the bar exactly, you just need to know you've got enough. And it's very easy to see. Very easy to see a scent rate monitor on the top there. If at any point I has to get an alarm on the rebreather, the machine would alarm immediately and let me know. As you can see, let's just continue with our checklist just so I don't get told off. Complete the checks in handset, yes. Analyse our bailout gas cylinder and confirm it's appropriate, yes. And calibrate secondary O2 monitor if fitted, and the answer is not fitted. Super. So, that's my test complete. The rebreather has been built up from the beginning, it's been assembled, and it's been tested. I can be confident the machine's working. If the machine didn't start up, it would be for an honest reason. This machine's job is to not stop you going diving, it's to take you diving, but in a safe way. If something on this machine fails, it's a genuine reason. People get themselves very frustrated because they think they did everything perfectly, but the machine doesn't start. It might be because one of your cells is a little bit cold or damaged or not working properly. It might be you've got the wrong diluent. It might be your battery isn't charged. But whatever it is, it's not a safe reason to go diving. And that's frustrating for some people. On the JJ, it does not care. It doesn't care if I put no scrubber in, if I've got no oxygen, it doesn't care anything. It doesn't care if I've calibrated it. I can go diving with that rebreather in the worst possible condition and it doesn't mind. This rebreather does mind. And one of the things that I like to tell my students about this rebreather was, in the very early days, there was an incident in Sweden where somebody actually died on the rebreather. And that sounds like a negative thing, but the machine itself did everything it possibly could to keep the diver alive. So, I'm not sure, let's take the story as the way I was told it. I can't guarantee it's 100% true, but basically, the diver put the rebreather on and entered the water with everything off. Okay, the gases were on luckily, but the machine was off. He went in, the machine recognised it was in the water and started up immediately. Okay, now I believe what happened was on the land, the guy had tried to do the pre-dive startup, but it wouldn't start up because of low battery. So he tried and tried and tried, and low battery, low battery, low battery. Bearing in mind, you can't just go to a shop and buy batteries for this. You need to put this battery into a charger that's in the wall and leave it for a good, at least 20-30 minutes to get a decent dive out of it. So he couldn't just change the battery. He entered the water with the machine off and the battery in a low state. The machine decided to turn itself on to try and maintain life. It turned itself on and started actuating the solenoids. However, it was beeping, flashing, alarming all the time to let the diver know you're not in a safe condition, get out of the water. He didn't, he continued to stay underwater. The machine then recognised that the voltage it was drawing for the audible alarm and the vibrator were too much. So it shut those off and decided to focus all of its voltage on the solenoids. So keeping oxygen going to the diver, keeping the diver alive. And it did that for as long as possible. Okay. It then started to shut down the handset and all the other systems, maintaining only the solenoid. And it was the solenoid that kept going and kept going and kept going. Unfortunately, that diver still remained in the water. So no display, no HUD, no alarm, that all switched off. And in the end, the battery died. As soon as the battery dies, it fails to add oxygen, and eventually the guy breathed the loop until it was hypoxic. But the positive message we can draw from that is that because this rebreather is designed in such a way that all of the electronics are doing its absolute best to make sure that you get the safest dive possible, it will always try to keep you on the safe side. Now, we know if we always are on the safe side of caution, quite often we may not make the dive because something isn't working, especially if you do not look after this rebreather. This rebreather was just serviced. You saw, I didn't do anything out of the ordinary than setting up any of the other rebreathers. I went through its 54 self-tests immediately with no failures. And that's because it's kept in a good condition. Now, if you were to go and spend £8,000 or £10,000 on anything, you'd want to keep it in good condition, but we don't see that throughout the rebreather market. The rebreathers are not very well looked after. They're chucked in a hot car after a salty dive, left for 2 or 3 days, and then cleaned a little bit, chucked in storage, pulled out the box and expect it to work straight away. Now, the JJ will cope with that. The SF2 will cope with that. The Revo will cope with that. But the Poseidon, because it's sensitive electronics that are doing lots of monitoring, it doesn't really cope so well with that. So it means that you need to look after your rebreather. However, all rebreather manufacturers will tell you you should look after your rebreather. Going into the water with a rebreather that's not clean, not got good battery life, and not safe to dive is not a good idea at all. So we're in the same boat. It's just a case of this machine's a bit more sensitive to the being maltreated, let's say. So this is the standard, the 6 and 7 rebreather. This is the 7 because it's got the 7 electronics, but everything else about this rebreather is the 6. The mouthpiece is the 6, the counter lungs are the 6, the round pack and everything's the same as the 6. If I was to go for a 6 head, there's different types of 6 heads on the market. I can have one that's limited to 40 meters, or I can have one that's limited to 60 meters. That's based on the software that was inside it at the time. Some 40 meters can be upgraded to 60, but there's not many of those around anymore. If you get a 40 meter one, great, it'll be fantastic for recreational diving with a green battery. If you get a 60 meter one, you can put a green recreational battery in for 40 meters. You can put a blue battery in for trimix, so 48 meter trimix. You can put a white battery in for 60 meter trimix. With the 7, we can put the black 100 meter battery in, and we can limit it by software. So if I want to put the black battery in, and I want to go into the software via Bluetooth and say I want it to limit me to 40 meters, and I want it to limit to no decompression, when I start to reach 40 meters, or actually go over 40 meters, and when I start to reach my no decompression limit, this machine will act like the green battery machine. So it will alarm and allow me those limits to be recreational only. I can then increase the depth limit as I go. So if you were to buy the black battery, that's probably the best because you've got that scope of just editing it with software alone. Yeah, no worries, Luke. Nice for you to join us, and you can see the rest later on. Does anybody else have any questions about the Poseidon rebreather? What I can tell you, it's super light, very easy to use. The type of people we train with this are things like camera people, people who just want to enjoy their life underwater, who are not very technically minded from time to time, want something very light and easy to travel with. Because you don't need to do a great deal. You can sit there, look through your viewfinder very happily. As soon as something goes wrong, you'll get beeping and flashing. Now, that's not to say you shouldn't know your PO2 and know what your rebreather's doing. It's just that this machine's a little bit easier at warning you when something goes out of standard. Yeah, I love the easy to read numbers on the handset. Yeah, so even from that distance, you can probably see what the handset says. It is a bit like a ping pong bat. It does get a bit of stick. But in reality, for most of us that get a little bit old with the glasses, it's easier to see. Now, let's talk a little bit about some of the really fancy upgrades we can get. The most fancy upgrade we can get is the M28 computer. The M28 computer is a really nice, full colour, got GPS in it, got maps in it, can play video games on it, really high quality computer that fits on the wrist and plugs into the system. You can plug it in place of the handset, you can plug it in as well as the handset, or you can plug it into a third cell holder. So there's lots of different ways you can connect it. The other options that we can add to this rebreather are something called a solid state cell. Now, we talked about these galvanic oxygen cells that are inside most rebreathers. They take oxygen, they have a finite amount of consumables that get used up generating our voltage, and as that happens, the cell can die. They're very, very sensitive. If you drop a cell on a table, you've probably damaged it. That's how kind of sensitive they are. They are the weak point of all our rebreather. Bearing in mind, when we go technical diving, we have one backup. We have a primary mask and a backup. We have a primary regulator and a backup. We have we have a lost gas plan if we lose one gas. So we always have one failure mode. Why then in the rebreather do we have 3 cells? We have 3 cells because they're not so reliable. And we can't just check one from another. We want to use this voting logic to have 2 that are right to check against another. And that's so the cells are technically the weakest point of our rebreather. For instance, the Revo's got 5. Some divers with a Poseidon with 2 will add another 1. Some divers with an Inspiration with 3 will add another 1 to bring it to 4. And so they've got as many of these cells as possible because they're the weakest link. Poseidon have developed a really new technology called a solid state cell for a rebreather. Solid state cells have been around for a bit in medical applications, but for a rebreather, it's kind of a new application. And a solid state cell is a factory calibrated digital device. It detects oxygen digitally. So it doesn't need this kind of consumable inside itself. The only consumable inside itself is the LED. The LED's got so many hours for it'll run by the manufacturer, and then it'll probably stop. but it might also go twice as many hours. We don't know. It's just given a limit by the amount of hours that LED is valid for. But basically, that LED inside lights it up and it detects with a sensor the amount of oxygen inside the rebreather. They've become factory calibrated, so we don't have to worry about calibration anymore. We don't have to worry because if we put the wrong gas on, we don't have to worry that we can calibrate badly because the machine was calibrated the cell was calibrated in the factory. So no matter what gas I put on, it will always know what it is. It's also good for something like 10,000 hours. So when I have to change the cell inside these rebreather every year, that's kind of £80 per cell, 2 cells. If you've got 5 cells inside your Revo, it's an ongoing process of replacing cells, but that's costly. Whereas a solid state cell, 10,000 hours of diving, sticking inside the machine and off you go. They're so accurate that Poseidon reckon you could probably dive with just one. If it fails, you bail out, of course, but generally it's so accurate and so quick to react and respond that it's going to leave galvanic oxygen cells in its wake. Now, at the moment, it's a little bit expensive for the cell, the C-pod, the little holder that it's got, and the M28 you're going to monitor it with, is going to set you back around about 3,500 English to have this solid state cell built inside the rebreather. But I will tell you, I think they're the future of oxygen monitoring. When Shearwater or one of the other big players come up with a solid state cell application for the rest of the rebreathers, I think we'll be in a really good position because the solid state cell has the potential to make rebreather diving exponentially easier and safer. The Poseidon cell is available for other rebreather manufacturers to buy if they want. I know that. But it does, I think, got to come with a Poseidon handset. So I think a few of the rebreather manufacturers are a little bit wary of bringing that technology to their machine. I do know also that other manufacturers like Van de Graaff and stuff have been working on designs of their own solid state cell. Of course, like everything in the world, you need to make sure that patents aren't broken and intellectual property rights aren't broken. So I think it's a bit of a process. We're not there yet. Also, how's the testing happen? We're a very small community of rebreather divers. There's very few rebreathers on the market compared to lots of other products. When we get these things in, we need to make sure that they work in this very intense environment. Remember that we're at ambient pressures, up to 14, 15 bar sometimes, in a very moist, humid environment, potential for flood, seawater, all the spit and other contaminants that go inside the rebreather, and rebreather divers aren't exactly the cleanest bunch anyway. So you've got to imagine that cell is operating in a super harsh environment. To make sure that electronics operate in a super harsh environment takes quite a bit of testing. So we could see potentially in the future a bit of these cells coming, but it might take time. The Poseidon cell, I have to say, got one, use it a lot, works absolutely brilliantly. It's very fast and very smooth. From January, Poseidon launched the rebreather so that now you can get solid state cells built into the head. So rather than having the standard galvanic cells in the head, you can put 2 solid state cells inside the head. Not aware of the pricing, but I imagine it's not super cheap. That technology is going to take some paying back. But that means you've got now 2 cells that are factory calibrated, don't need calibration, don't need you to think and worry about them. They're just going to sit there doing their job. And so that's a really great step in my mind. We just need the price to come to somewhere that's a little bit more acceptable. And of course, be available on other rebreathers would be a great addition. I can't imagine people being able to make mistakes on this unit, so what mistakes can they make? So the mistakes they can make are things like not putting that top hat on or leaving the O-ring out. That was a bad mistake. The other mistakes people make is complacency. Unfortunately, making something idiot-proof means that you also make better idiots. So this thing is, I would say, you have to try pretty hard to kill yourself on it. But generally, some people manage it. And it's not because they're stupid. It's not because they wake up every day and decide they're going to kill themselves. It's just that because it's easy, you can kind of get a little bit complacent and not check so many things. The main thing is, though, that if you're monitoring this rebreather and it's going through its startup test, you're probably going to be on the safe side. The frustration of it not working quite often means people will go into the water with it not in an ideal condition and not working properly, which means it's compromised and it can't do its job properly. But generally, the machine is very, very safe. Some of the stupid mistakes people make are leaving the mouthpiece open and flooding it, but that's common to every rebreather. Jumping in with the gases off, that's common to every rebreather. Even though when you turn them on, it gets you to go through the self-check, it doesn't know now if I shut them down. I jump in the water and I use gas, it'll see the pressure drop and then it will alarm, but it doesn't know that I've turned my gas off. And if it's up here, I might not be able to turn it back on again. So I should come off the rebreather, of course. That's another problem. Other mistakes people can make, not checking their O-rings, that kind of thing. You can get, you know, especially with the battery, if the battery floods underwater, you're going to lose all of these cool systems that keep you safe. The rest of the machine is pretty bulletproof though, you know. If I was to drop this rebreather off this table, it would still survive. It's strong, you know. It is a tough rebreather. It does its job fantastically well, and a lot of people like them. The one thing I'll say that's maybe interesting about this rebreather at the moment is you can pick a Poseidon 6 rebreather up, so the model before this one, with most of the same features. It doesn't have the Bluetooth, so you have to use infrared to connect to the rebreather. But if you use it in the recreational range or the limited deco range, it's a fantastic rebreather, because you're only talking about £1,500 outlay. 15 to 2,000 quid, you could buy one of these 6s on the second-hand market, get it serviced up and have a rebreather that is fantastic for kind of normal diving. In reality, the amount of people that go to 100 metres every week is very small. The amount of divers that go to 25 to 50 metres every week, that's much bigger. And the Poseidon 6 rebreather will fit into that range really perfectly. There's plenty of them on the market, so there's plenty of spares available. The servicing is every 105 weeks, so it's every 2 years. And that's a relatively low cost. So a 2-year service interval makes it nice and easy as well. Training is simple. You can either do a recreational course, so you stay with no decompression with no trimix in the recreational range, or you can go on and you can do a decompression course with trimix. Just a minute. Stop that, Will. So, yeah, the training is nice and simple. In the recreational range, generally, the only skill you need to learn is buoyancy control and bailing out. There's no complicated buttons to press, manual addition to do, semi-closed skills. It's very, very simple. Once the gas is on and the machine's turned on, you're going to breathe in and out, and if you're not get a situation where the machine has failed, it'll alert you, and then you just move the switch to the bailout position. Well, sorry about that, Will's cleaning something, so it's making a noise. Last step with this rebreather, actually, I just forgot, is to put this nice fancy case on. The fancy case just protects it. It's got some steel bars there. You can attach batteries and stuff to it, and it clips on the back just to make the machine look nice and neat. So we'll push it into place with the clips. This is a part of Se7en only, so that'll go on the back there. Right, next step. Let's see who we've got. Are the solid state O2 state sensors reliable / bug tested? So, in my personal experience, they're very reliable. I've not had a single failure from mine, and mine is close to 3 years old now. 2 years old now. Yeah, maybe 2 years. I was one of the first people to get one, and it's been fantastic ever since. I've not heard of anybody on the market having problems with them either. And that might be that not many people have got them, and it might be that I just don't hear it. But generally, from my experience and what I've heard, they're super well tested. Poseidon, when I was there in Sweden the other week, in February, told me that their solid state cell is a fantastic tool, and they don't see almost any returns. With every product you'll see some small returns, I'm sure, but they're saying it's a fantastic product as well. Suppose those solid state cells are not for yours? No, not yet, Tony. I think, you know, the other rebreather manufacturers in the marketplace are going to want to make sure that their really solid products aren't affected by putting something in that may not be as perfect as the rest of the machine. So they're going to need real confidence in those solid state cells before they start to add them to a design that already works in a very, very strong way. Poseidon, obviously, they were the people who developed it, so they have the confidence in those cells to put them directly into their machine. The other rebreather manufacturers might take a bit of persuading, and certainly there need to be an affordable price. If you imagine that the JJ or the Red Bear, like your machine, now needed £4,000 worth of cells fit into it, okay, you wouldn't need to buy any new cells for the next kind of few years, but that's a big cost on a new rebreather. So they would need to find a way in which they get a trade price that wouldn't make their machine overly expensive in the market as well. Why don't other units just use these solid state sensors? Honestly, Sam, I don't know. Poseidon own the technology as it is currently, so they've got a patent on their version of it. I believe other manufacturers are working on their own versions of the technology that don't infringe on the patents, but Poseidon have, as far as I'm aware, offered it to other manufacturers for sale. Now, there might be reasons that those two manufacturers don't want to work together. There might be reasons that the cells might not be compatible. If you imagine, that solid state cell needs power. So to power that cell and to get the digital signal back, you would need to change the wiring of every other rebreather on the market. Every other rebreather in the market either has a coaxial plug or a 2-pin Molex, and that's just a signal in and out. It's not a digital signal at all. It's just a voltage being read by a board somewhere else. So they would need to completely redesign and rewire the electronics of all the rebreathers. That means probably, again, I'm not an expert, but probably they would have to re-CE certify all of their rebreathers, change all of their structure for the calibration process, and change all of their procedures. So it's not a 5-minute overnight job. It's a big process, and it's potentially very, very expensive. If it's going to be expensive to do and expensive to the end consumer, that's likely to put their rebreather in a position where it's unaffordable, so they might not be doing it for that reason. I think it's a matter of time. Like everything in the world, you see that something is developed, it's a fantastic product, but it doesn't reach the end consumer too quickly because it's got to go through stages of the technology getting cheaper, confidence being built in it, and accessibility to everybody else so that it can get out in the marketplace. And that's probably why. What else have we got? I think that's it for questions. So, thank you very much for joining us today for our Poseidon build. Next week we're going to run through the Prism 2. I also have, luckily, coming from Germany, a Mares Horizon rebreather coming for the build after that. So it's going to be Hollis Prism 2 next week, which is a really fantastic rebreather. It's going to be the first rebreather we see with a radial scrubber built in as standard. It's going to be a first rebreather from one of the major manufacturers. Okay, so kind of the major open circuit manufacturers have put their weight behind this rebreather. And then the week after that, we're going to see the Mares Horizon semi-close rebreather. So it's not actually CCR, it's an SCR. And the Mares Horizon is a really bit of a game changer for recreational diving. So that'll be an interesting one to watch. Thank you for your time, guys. And if you want to watch this video, of course, it'll be posted on our Facebook and shared everywhere a little bit later on. So catch you all later. Thank you.